something strange in your neighborhood. Who you gonna call?
Gilbert Newton Lewis. What's up, everybody? Welcome back to Doodle Homework with your girl, Doodle Kara. Today, we are looking at how to draw the beloved Lewis diagram. You may also hear it referred to as the Lewis dot diagram, the Lewis structure. It's kind of like the various sayings of crowns, crayons, crumbs. It's all the same thing. In essence, the use for these diagrams is to show the unpaired electrons of various atoms and how they come together when bonding. The basics of Lewis diagrams can be easy at first. For example, if I have a hydrogen and a bromine, I may already know their valence electron numbers just by reading the periodic table. In Lewis diagrams, you represent those valence electrons by using dots around the symbol. Oh no, what is that? Is there a chemistry emergency? No, you just forgot to mention that valence electrons are different from total electron number. What are you trying to do? Confuse the kids? All right, get out of here. All right, so my manager doesn't come back. Just so you know, valence electron number and total electron number are two completely different things. Total electrons is every electron in every orbital of that atom. Valence electrons are our outermost energy level electrons that are used specifically for bonding. There. Is that better?
Yes, thank you.
So anyway, like I was saying before with hydrogen and bromine, to make their Lewis dot diagrams, I simply draw one dot around the symbol until I run out. Since these are valence electrons, the most I can ever have around a symbol is 8 due to the octet rule. All right, so if I want to combine hydrogen and bromine, I can just simply combine them using a Lewis diagram. As you can see, this shows the hydrogen and bromine now sharing the 2 electrons. As in life, things can get slightly more complicated, and so we have some rules to help organize and structure how to make Lewis diagrams, specifically for those that get a bit more complex. The first step is to determine the total number of valence electrons among all the atoms listed in the compound. For right now, we're going to assume all of them are neutral. We'll look at ions later on. The second step is to draw a skeleton structure or expanded structure of the molecule, putting the least electronegative atom in the middle. We connect them initially with single bonds. However, we can always go back and add in more bonds where needed. The third step is to add in lone pairs to the most electronegative atoms so they have a full octet. Remember, if we are keeping things neutral, everything should have 8 electrons bonded. The last and fourth step is to place all remaining lone pairs and start rearranging lone pairs in order to make extra bonds if needed to fill the octets of all atoms. All right, let's put to work everything we just talked about in an example of butane. Butane has a formula of C4H10. For this example, we will follow the 4-step method. First, count the total valence electron number. Carbon has 4 valence electrons and hydrogen has 1. We're going to multiply this number of valence electrons by their subscript. So for carbon, it'll be 4 times 4, which gives us 16, plus 1 times 10, which gets us a total of, if you add 16 plus 10, 26. So this means we have 26 total valence electrons to distribute in our molecule. Next, we're going to draw out the skeleton structure or expanded structure. Hydrogen will never be our central atom. So by default, that makes carbon our central atom. If we counted up all the single bonds we just made between carbon and hydrogen, we would notice all valence electrons are used, meaning there are no more lone pairs we can add or extra bonds for double or triple bonds. This means that we have completed our structure and we can go ahead and draw in our Lewis structure, which shows those electrons being shared. Okay, so in all fairness, that was also a little basic. In the next example of carbon dioxide, we'll look at some competing electronegativity and lone pair distribution. So carbon dioxide's formula is CO2. So the first step would be to count up the total number of valence electrons that we have. In this case, again, carbon has 4 valence electrons and it only has a 1 for its subscript, so it would be 4 times 1 plus oxygen, which has 6 valence electrons, times its subscript of 2, doing 6 times 2, giving us 12. We add both those up, so 4 plus 12 gives us 16 total valence electrons. Our next step is to start drawing out that skeletal structure. So again, we're just going to go ahead and add single bonds between our atoms. Carbon is the less electronegative atom here, so it goes in the middle, and we do single bonds to the 2 oxygen going out of the carbon here. Next step is to add in those lone pairs to the most electronegative atom, so we're going to give all pairs to both of the oxygens. If we do our subtraction in this case, we would see that at this point we actually do use up all of our valence electrons. However, carbon has still not fulfilled its octet, which means this cannot be our final structure. So in our next step, we take a lone pair from each of the oxygen and build a bond to create a double bond to the carbon. This is now our completed structure. We can then go in and draw in these electrons in the Lewis diagram to show both the double bond to each of the oxygen as well as the oxygen's lone pairs.